In this model, we will be discussing some other properties of the solutions. After this model, you should be able to describe what a colligative property is and explain the difference between the effects of non-electrolytes and colligative properties. Also, you will be able to calculate the vapor pressure of a solvent over a solution. You will also calculate the boiling point elevation and freezing point depression of a solution. And finally, you'll be able to calculate the osmotic pressure of a solution. Let's start with colligative properties. Colligative properties depend only on the quantity, not on the identity of the solute particles. And we have different type of colligative properties. One of them is the vapor pressure lowering, the boiling point elevation, the freezing point depression, and the osmotic pressure. The vapor pressure. Because of the solid-solvent intermolecular attraction, higher concentrations of non-volatile solute make it harder for solvent to escape to the vapor pressure phase. Therefore, the vapor pressure of a solution is lower than that of the pure solvent. Okay, let's see this example. Here we have a solvent that is in a closed container, and the solvent that is volatile is this one in blue. Um, some of the molecules of that solvent will go to the gas phase that is here. So you can see that some molecules are in gas and there are others that are in a liquid. And they're going to reach an equilibrium where the same amount of molecule that goes from liquid to gas is the same amount of molecule that goes from gas to liquid. So for example, if we have 10 molecules that goes from the gas by the liquid, you're going to have 10 of the gas that are going to go to the liquid. Okay, so there's an equilibrium between these two phases. Okay, now because you produce a gas here, that gas that is in a closed container is inducing a pressure over the surface of the solvent. That pressure, it's called the vapor pressure. Okay, so now what happens if we add a non-volatile solute? Okay, if we add a non-volatile solute, that means that now we have more molecules of the solvent that is going to stay in the liquid because they're going to interact with that non-volatile solute that we add. And because of that, we're going to have less molecules of the solvent in the gas phase. And because we have less molecules in the gas phase, the vapor pressure is lower. Because remember that the vapor pressure is induced by the molecules that are in the gas phase. So that's why a pure solvent will have a higher vapor pressure than a solution, because in the solution, some of the solvent, molecule of the solvent will interact with that solid and couldn't escape to the gas phase. We have a law that is called the Raoult's law that is going to help us to do a relation between that molar fraction or the amount of the solid with the vapor pressure. So the vapor pressure of a volatile solvent over the solution is the product of the mole fraction of the solvent times the vapor pressure of the pure solvent. So here we have that equation. P is pressure, and this is the pressure of the solution, will be equal to the molar fraction of the solvent. Remember that molar fraction is moles, in this case moles of the solvent divided by the total moles of the solution. Okay, that as we saw in our last in the previous model. And this is the vapor pressure of the pure solvent. This zero means pure. Okay, so the vapor pressure of the solution will be equal to the molar fraction of the solvent times the vapor pressure of the solvent. In ideal solution, it is assumed that each substance will follow the Raoult's law. Okay, so remember that this is an equation of three different variables. So if we have two of them, we can obtain the third one. So we have the vapor pressure of the solution and the vapor pressure of the solvent. We can determine the molar fraction, okay? Or if we want to determine the solvent, the pressure, vapor pressure of the solvent, we can do it by knowing the molar fraction of the solvent and the vapor pressure of the solution. So remember that it is not just to determine the vapor pressure of the solution. We can determine also this variable or this variable. But because we have three, we need two of them to determine the third one. The boiling point. Remember that the boiling point of a liquid is the temperature at which its vapor pressure is equal to the pressure of the gas above it. So here we have an example of a pure solvent, and usually the pressure that is exerted over the surface of the liquid is called the atmospheric pressure. So we need to add heat, so in that way the molecules of the liquid could create this gas and create enough vapor pressure to be more than the atmospheric pressure. In that way, at that point, the liquid will boil. Okay, so because at that point you have enough molecule of the gas to exert that atmospheric pressure. So if in the case of when you add a solid, because you have more molecules interacting with the solid, you're going to have less of these molecules in the gas phase, so you need to add more heat. So that's why the boiling point of a solution is usually higher than the boiling point of the pure solvent. Okay, and we can see that in the next figure. So the boiling point elevation, since the vapor pressures are lowered for solutions, it requires a higher temperature to reach atmospheric pressure. Hence, boiling point is raised. So here we have a diagram phase. Remember that in the diagram phase we have the three states of the matter: solid, liquid, and gas. And these are the borders that usually are between two phases. And in this case, this border represents the boiling point because it's the border between the liquid and the gas, or the condensation points. It all depends where you come from. If you go from the liquid to the gas, is the boiling point. If you go from the gas to the liquids, is basically the condensation point. So we are talking here about the boiling point. So we are talking about this border, but specifically at 1 atmosphere, that is basically the standard pressure. So here we see that the black border represent the pure solvents and the blue borders represent the solution. Okay, so these are the boiling points for the solution. And if we compare the boiling point of the solvent at 1 atmosphere with the boiling point of the solution at 1 atmosphere, this one of the solution is higher than this one. And we have a difference in the boiling point. Here we have a delta TB, that is a difference in the boiling point temperature. So let's see what happens to the freezing point of a solution. So the construction of the phase diagram for a solution demonstrates that the freezing point is lowered while the boiling point is raised. So here the freezing point is when you go from the liquid to solid. So we are talking about this border. Okay, this is this represent the freezing point, but also represent the melting point. So if you go from the liquid to the solid, we are talking about temperatures of freezing temperature. But if you're going from solid to liquid, we're talking about the melting point, okay? But in this case, we're talking about the freezing point. So remember that the black border represent the solvent and the blue one represent the solution. As we can see here, this down here is temperature, this is pressure. So for the solution, the freezing point is lower than the freezing point for the solvent. So we have again here delta TF, in this case the delta of the freezing point due to the presence of that solid. So the boiling point elevation and the freezing point elevation, the change in temperature of any of those is directly proportional to the molality using the Van Hoff factor. So in this case, this represents the molality. Remember that is basically the amount of the solid. It takes in account the amount of the solid. So we can see here that that change in temperature will depend on the amount of the solid. So that's why the boiling point elevation, the freezing point depression, and also the vapor pressure, they are considered colligative properties. Okay, that's why, because is going to it's going to depend on the amount of the solid. So here we have basically the the formula, okay, to determine that change in temperature in the boiling point specifically for a solution. So the change in temp in the boiling point temperature will be equal to the boiling point temperature of the solution minus the boiling point temperature of the solvent, and this will be equal to I times Kb times M. And for the freezing point, that change in the freezing temperature will be equal to the freezing temperature of the solution minus the freezing temperature of the solvent. This will be equal to minus I, Kf, and M, where I basically is of the Van Hoff factor. Okay, the K, if it's Kb, is called the molar boiling point elevation. For this one, the Kf is the molar freezing point depression constant, and M is molality. Okay, so here this is basically a table with some constant show here, and also the normal boiling points for those solvents. Okay, you don't have to memorize all of this. Is just to for show you some examples of the constants, but you need to understand how to use this equation. So this represents the change in the boiling point, and this is I. We're going to talk in the next slide about the I, the Kb, and the molality. So here we have 1, 2, 3, 4, 5. So we have five um, variables. So we need four of them to determine number five, or to calculate the fifth one. Okay, the same thing here. So we can know, for example, the temperature of the solution, the temperature of the solvent, and the I and the M, and we can calculate the constant, the molar freezing constant. Okay, so remember that this equation is not just to determine delta TF, but also help us to determine maybe the Van Hoff factor, or the constant, or also the molality of the solution. Okay, so we need to have all the other information to determine one of them. So the Van Hoff factor, the I, what is this? It takes into account the dissociation in solution. So theoretically, we get two particles when sodium chloride is dissociated. So when sodium chloride is in solution, the Van Hoff factor is 2, because sodium chloride is an ion, is an ionic compound, and in water it's going to dissociate it. Okay, you're going to separate the cation from the anion, so you're going to have two particles. So that's why the sodium chloride in solution has a Van Hoff factor of 2. In fact, the amount that particles remain together is dependent on the concentration of the solution. So basically, this is a different type of experiment when they found the expected value for the Van Hoff factor. So for sucrose, it's 1. Sodium chloride, this is an ionic compound, so we expected that in water is going to dissociate, so we're going to have two ions, the sodium and the chlorine. Here we have the potassium sulfate. Potassium sulfate, we have 2 potassium, and the sulfate by itself is an anion. So we have sulfate, 1 ion, and potassium, we have 2. So we expect that the Van Hoff factor will be 3. And we have here the magnesium sulfate. Magnesium is 1 cation and sulfate is 1 anion. So we expect to have the solution of magnesium sulfate has a Van Hoff factor of 2. Okay, let's talk now a little bit about plants. The plants needs to eat. One of the way they produce their own nutrients is through photosynthesis. And to do that, they need sunlight, okay, to create sugars, okay, so that sugar will help them to grow. But also they can have those nutrients from the soil. And to obtain nutrients from the soil, they use the roots. These roots, they have like a membrane, okay, covered by a membrane, and that membrane sometimes has like little doors that is called transporters, and those transporters helps to allow nutrients from the soil as sodium, phosphorus, potassium to goes through those transporter and get into the roots so the plant can eat. And also those roots can absorb water, okay, from the soil, and that water goes through those membranes but in a different way as the nutrients. Okay, the nutrients goes through those transporters, but the water crossed that membrane due to a mechanism that it's called osmosis. So the osmosis, some substances form semi-permeable membranes, allowing some smaller particles to pass through but blocking larger particles. The net movement of solvent molecules from solution of low to high concentration across a semipermeable membrane is osmosis. So, osmosis is when you have a movement of solvent from one side that has a lower concentration of any solid, and when that solvent goes through the other side, okay, through this semipermeable membrane of high concentration, that movement it's called osmosis, and the applied pressure to stop it to stop that movement it's called the osmotic pressure. So here we have this in the initial part, we have water in the left, and here in the right we have the solution, and between them we have the semipermeable membrane. Okay, so some of these molecules of water will go through this semipermeable membrane to the side where you have a higher concentration of the solid. Okay, so in that way, the water is going to go through the right, and this column is going to increase. Okay, so you're going to have a higher volume here in this side through this side. So that is called osmosis. Okay, when this movement of water goes through and it reaches an equilibrium where the same amount of molecules from water goes to this side and that amount of molecule of water goes to the other side. So it's an equilibrium, okay, of water. Now, if we apply the pressure in a way that the levels of both arms is equal, that pressure that we apply is called the osmotic pressure. Okay, so that pressure that we apply so we can have the same level of both arms, that pressure is called the osmotic pressure. So the osmotic pressure is a colligative property. Okay, so it is going to depend in the amount of solid that we have. Here, this is osmotic pressure is equal to I. This is the Van Hoff factor times N over V. This is mole volume, and mole over volume is molarity. Okay, so the osmotic pressure is equal to the Van Hoff factor times the molarity times R, the constant, and times the temperature. So if two solutions separate by a semi-permeable membrane have the same osmotic pressure, there is no osmosis between those solutions. Okay, so we have different type of solution and osmosis. So we have, for example, the isotonic solutions where same osmotic pressure, solvent passes the membrane at the same rate both ways. So you don't have there basically an osmotic uh, osmosis. You have both are the same osmotic pressure. You have a hypotonic solution where the lower osmotic pressure, so the solvent will leave this solution at a higher rate than it enters to the solution. And the hypertonic solution is a higher osmotic pressure. This is when the solvent will enter this solution at a higher rate than it leaves him. Okay, so in the isotonic solution, we have the equilibrium between the two solutions. The hypotonic solution, this one is when the solvent will leave the solution at a higher rate than it enters to the solution. And the hypertonic solution is when we have a higher osmotic pressure because the solvent will enter to this solution at a higher rate than it leaves that solution. So I'm going to show you here an example of a cell. This is called the blood cell. The red blood cells have semipermeable membrane. If stored in a hypertonic solution, they will shrivel as water leaves the cell because if it's a hypertonic solution, you have a higher concentration of solid in that solution. So the water in the cell will leave the cell, and this is called crenation. Okay? If you store it in a hypotonic solution, they will grow until they burst because you have going to have a higher concentration of solid inside the blood cell. So the water will go through that membrane inside the blood cell and it's going to burst. And this is called hemolysis. So here we have the red blood cells in a isotonic medium. Okay, we the same amount that is going inside the cell is the same amount that is going out the cell. Here we have the crenation example. So water from the cell is going out to that high solid concentration. Okay, it's going to that hypertonic solution. And the hypotonic solution, because the solid is higher in the blood cell, you're going to receive is the water is going to go inside the red blood cells and will grow until they burst. So with that, we finished this model 13, chapter 13, properties of the solutions.